Hello everyone, I am Ümit Alkuş. In this video, we will solve one problem in chapter 28. The triangular loop carries a current I equals 6 amperes in the direction shown in the figure. The loop is held fixed on the xy plane. There exists a uniform magnetic field of magnitude B equals 18 millitesla in the negative y direction. In the figure, the length on the x-axis is A equals 30 centimeters and the y component is 20 centimeters. In unit vector notation, determine A, the magnetic force on each wire segment. Magnetic force on a current-carrying wire whose current length vector is L due to the magnetic field B is calculated by the formula I times L cross B. And the direction of the magnetic force is found by the right-hand rule. First, we label each wire segment as 1, 2, and 3. The length vector L1 is obtained as A I hat plus B j hat. The length vector L2 is obtained as 2B negative j hat. Finally, the length vector L3 is obtained as negative A I hat plus B j hat. The magnetic force on segment 1 is I times L1 cross B. L1 is A times I hat plus B times j hat, and vector B is B times negative j hat. The first vector product gives us negative I times A times B I cross j hat, and the second vector product is negative j hat cross j hat, which gives 0 because the vector product of parallel vectors is just 0. We know that I hat cross j hat is k hat. Now we put the numerical figures into the equation. As a result, we obtain 3.24 times 10 to the negative 3 newtons with direction negative k hat. In the figure, it is shown inside the paper. For segment 2, since magnetic field is parallel to length vector L2, then because of the cross product, the magnetic force on segment 2 is just 0. The magnetic force on segment 3 is I times L3 cross B. L3 is negative A times I hat plus B times j hat. And vector B is B times negative j hat. The first vector product gives us I times A times B times I cross j hat. The second vector product is negative j hat cross j hat, which is 0. As you remember, I hat cross j hat is k hat. So F3 is I times A times B k hat. If you notice, it is the negative of F1. Therefore, F3 is 3.24 times 10 to the negative 3 newtons in the direction k hat. It is shown in the figure as towards U. This is an expected result because, as you were told in the class, the net magnetic force on a current-carrying loop is 0. B. Determine the magnetic moment of the loop. Magnetic moment, denoted by mu, has the formula n times I times A U hat, where n is the number of turns, I is the current, A is the area, U hat is the direction. Here we have just one turn. The area of the triangle is 2b times A over 2. So B times A. Finally, the direction is determined by the right-hand rule. Therefore, it is negative k hat. With these expressions, magnetic moment is I times B times A negative k hat. We know the numerical values. Therefore, the magnetic moment has the magnitude 0.63 amperes meter squared and the direction negative k hat. C. Determine the torque acting on the loop about the x-axis. The torque, denoted by tau, has the formula mu cross B. Mu is I times A times B negative k hat, and magnetic vector is B times negative j hat, which gives I times A times B times capital B k hat cross j hat. K hat cross j hat is negative I hat. Now we can insert the numerical values into this equation to obtain 6.48 times 10 to negative 3 Newton meters negative I hat. D. Determine what will happen if the loop is set free to rotate about the x-axis. Since the torque is in the negative x direction, the loop starts to rotate around the x-axis towards the screen. Or as the final remark, it oscillates around the x-axis back and forth. Okay, that's all about this problem. Thank you for your attention. See you in the next video.